Dalton's law of partial pressure might be one of the easiest gas laws to comprehend. It refers to a mixture of gases. If you have a mixture of gases in a closed container and you want to know the total pressure, it should just be the sum of the pressures exerted by each individual gas. In other words, add them up. So if you've got 3 gases together in a balloon and you want to know the total pressure, you just add the pressure from each individual gas. You're feeling confident, aren't you? Now there's one thing that I'm going to add in here. It says a mixture of gases. I'm going to change that to fluids. Fluids are any substance where the particles can flow. So that would really involve either gases or liquids. I mean, liquid particles can flow, and if the particles can flow and move, they can collide with the walls of their container, which can create pressure. Now, that shouldn't be anywhere near as much pressure as a gas, but it may be something significant that we would want to include here. Now, let's a couple observations of ideal gases. And this term ideal gas has kind of snuck up on us a few times early in the study guide, and we're really going to focus more on it coming up very soon in your near future. But basically, here's the idea. The volume of the individual gas particles themselves is not important. If it were, the identity of the gas would be important. The identity of the gas is not important when you're doing calculations with Dalton's law. It doesn't matter if I have hydrogen, helium, and oxygen, or I could have hydrogen, nitrogen, and fluorine, or something crazy. The identity of the gas does not make a difference. What we're really looking at is the amount of collisions inside the container. That's what creates the pressure. The amount of collisions should be directly proportional to the amount of particles, not necessarily the identity of the particle. And again, if the identity of the particle were important, then we might have to think about things like intermolecular forces. Would that affect the amount of pressure exerted by a particular gas? If one gas had stronger intermolecular forces than another, that might affect the pressure that we see. And it's not going to be a factor. The intermolecular forces among the gas particles will not be a factor because technically these gas particles are so far apart that they're not close enough to have intermolecular forces be any kind of significant attraction between the particles. It's not going to affect their collisions, meaning it won't affect their pressure exerted. When we do calculations with Dalton's law of partial pressure, you'll often use something called a mole fraction. And again, this all makes total sense. Mole fraction is kind of like a percentage. It's moles of that individual gas divided by total moles in the container. So it is like a percent, but you don't multiply by 100. It'll be symbolized with this kind of Greek letter chi. It's kind of like an X. So think about mole fraction as like a percent, but in the end you won't use it as a percent. You don't have to multiply by 100. Mole fraction can be used with solutions where you might have like moles of solute divided by a combination of the moles solute plus solvent, total moles in the solution. It really is like the part divided by the whole. So we can use this to calculate partial pressures of a gas in a mixture. So easy. Watch this. Check out the partial pressure of oxygen, observed to be about 156 torr in air, so a mixture of gases. The total atmospheric pressure is 743 torr. Calculate the mole fraction of oxygen present in the air. Well, notice that they don't give us moles. So sometimes people freak out and they think that they got to like use pervert or something crazy. But wait a second. The amount of collisions is what causes the pressure. The amount of collisions is directly proportional to the amount of particles in the mixture. You don't have to do this mole fraction with moles. You can also use pressure if it's in terms of a gas. So all I have to do here is say I have 156 torr oxygen divided by a total pressure of 743 torr. Total. You don't have to multiply by 100, you just plug her in your calculator. Let's say about 0.210. So let's say this mixture is approximately 21% oxygen. If 21% of the pressure is coming from oxygen, then about 21% of the particles or the moles are oxygen. So be aware that for gases, you can do this mole fraction without actually having moles. It's like the part divided by the whole when we look at mixtures of gases. With gases, the pressure is proportional to the amount of particles or moles. Here's another way we can use this then. The mole fraction of nitrogen in air is about 0.7808. Or in other words, it's saying that air is about 78% nitrogen. Calculate the partial pressure of nitrogen in air when the atmospheric pressure is standard, 760 torr. Piece of cake. So we're just going to use it kind of like a percentage, but that's why we keep it in the decimal, 0.7808. So it's about 78% nitrogen. So about 78% of the pressure comes from nitrogen, 760 torr. So we'll multiply. I'm going to leave 3 sig figs so it matches my other pressure. 593 torr. That's the partial pressure of the nitrogen. The pressure coming from the nitrogen collisions alone. Makes sense, right? Here's how we might use this in the lab. So we're going to collect a gas by what's called water displacement. And now we'll have something that's kind of like this. We're doing a decomposition here. We're heating some potassium chlorate with a manganese catalyst. This is kind of one of those goofy equations that you just kind of have to know. One of these decompositions that's relatively common. Potassium chlorate, or any chlorate for that matter, when heated, will always break down into the chloride and oxygen gas. And then we just balance it accordingly. So we'll need a couple of these, and a couple oxygen. That's an equation I would be relatively familiar with, and we did this one in the lab early on in the year. We took potassium chlorate, we heated it in a test tube, and to prove that there was oxygen gas, we added some kind of sugar like M&Ms or Skittles or something like that. And do you remember how it went like absolutely bonkers and it starts shooting off these purple flames? It gives off tons of energy. Well, the sugar compound is combusting in the presence of that oxygen formed. It's burning, which is why it gives off tons of energy. The purple flame is the flame test color of potassium. So there's still potassium chloride in your container, in your test tube or whatever you're using. And when there's so much heat surrounding it from that combustion, you'll see the flames turn kind of a purple color from the flame test of the potassium. All right, so in this case, we're not going to burn anything. We're heating the potassium chlorate, and we're going to let that oxygen gas bubble into a container of water. It's hard to collect gases in the lab, because often if you have an open container, the gas just escapes into the surroundings. So here's one good option. You fill a container completely with water, and then we flip it upside down into a big trough or another large container of water, so that the pressure of the water in the large container will kind of hold the column of water up inside your beaker, or we're going to use big graduated cylinders. And you may have even remembered kind of doing a lab like this in first year chem, where you used little butane lighters, and you kind of hold the lighter underwater and you bubble the gas up into a large graduated cylinder. As that gas starts to fill the container of water, it displaces the water. So eventually, we bubble in oxygen gas. This originally was all the way to the top, filled with water, but that water gets displaced by the oxygen or whatever the gas is you're collecting. So up on top here, we definitely have oxygen gas, but we're also going to have a very small amount of water vapor, because we know in a closed container, water tends to have a vapor pressure. We're going to need to take that into consideration if we want to know how much oxygen we collected. That some of that gas up in that sample is going to be water vapor. Piece of cake. Watch how this works. Let's get some data. Okay, so we have the solid potassium chlorate. There's the balanced equation. We did that correctly. We're going to heat it in a test tube and decompose it. We're going to collect the oxygen gas by water displacement. It tells me that the water is 22 degrees Celsius. That might be important in the end. The total pressure inside that upside down container where I'm collecting the oxygen gas, the total pressure is 754 torr. The volume of gas collected is 0.650 milliliters. And the vapor pressure of the water in that container at 22 degrees is 21 torr. Holy moly. Calculate the partial pressure of just the oxygen gas that was collected. And we also want to know the mass of the original sample. This is very similar to what we're going to do in the lab. We're going to do a reaction that produces hydrogen gas. We're going to bubble that hydrogen into water. And in the end, we're going to try to figure out how much hydrogen we collected. And we're going to have data really similar. We need to know the temperature of the water. In the lab, we're going to have to look up this. The vapor pressure of water is a constant. You look it up on a chart. It'll just give you different vapor pressures depending on the temperature, which we saw in the last chapter, that as you increase the temperature, you increase the vapor pressure. So we need to know the temperature of the water, and we'll assume then that the vapor is the same temperature, 22 degrees. So in the lab, we'll just look it up on a chart, the vapor pressure of water. Here's why we need that. If I want to know the pressure of the oxygen produced, I'm going to have something like this. Pressure total equals pressure of the gas. In this case, it's oxygen gas, plus the vapor pressure of the water. Well, if we want to do any kind of calculations that reference the gas collected, we really just want the pressure from the gas. Or in other words, we want the partial pressure of just the gas collected. We're not interested in the fraction of pressure coming from the water vapor. So we do a little calculation. It's super easy. The total pressure is measured to be 754 torr. We want just the pressure of the gas, but conveniently, we can look up the vapor pressure of water on a chart. We just need to know its temperature. And here they give it to us, 21 torr. Now this becomes a very difficult calculation. All we have to do is subtract off the pressure from the water vapor. The remaining pressure is coming from the gas collected. So P gas, pressure of the oxygen gas, in this case, is 733 torr. Bingo. That wasn't so bad, right? So the concept again is just that when you collect a gas by water displacement, not only do you have pressure coming from the gas produced, but there's also water vapor pressure in your container. And before we do any calculations in reference to that gas, we want to include just the pressure of the gas alone. So we subtract off the pressure from the water vapor. Now I think we can handle this. We want to know the original mass of the potassium chlorate sample. So I want to be able to do some kind of stoichiometry. I know the amount of oxygen produced. I want to go backwards and figure out the amount of potassium chlorate. Well, in order to use that 3:2 ratio in the balanced equation, I need moles of oxygen. But I think we have enough data to calculate moles of oxygen. We're going to use PerfNerd. I don't need that much room. Let's make sure that I got all my data here. PerfNerd! The pressure of the oxygen gas alone is 733 torr. Don't forget that. If we're calculating moles of oxygen, it needs to be just the partial pressure of the oxygen. The volume was 0.650 liters. We'll just measure that in the lab. We're going to solve for N moles. Since my original pressure is in torr, I'm going to use the R value in torr. This would be something that you can look up in the AP package. You do not need to memorize it, but do use the amount of figures given. So we're going to go 62.36, and the unit is torr liter per mole Kelvin. And you can put these variables in any order. It could be liter torr per Kelvin mole or whatever you want. And then finally, temperature must be then in Kelvin. So we'll take our 22 degrees and add 273. So we'll say 295 Kelvin. All of your other units must match the units of the constant. So actually, this is going to come up in the lab. We're not going to collect a full liter of gas. Our volume in the lab will be measured in milliliters. And we'll need to convert it to liters before we can PerfNerd because of the units used in the constant. All right, so let's see what we got. We plug this in our calculator. I think I'm going to go with about 3 sig figs and say 0.0259 moles of oxygen gas. Well, now you see where this is going, right? We can use all this stuff in stoichiometry, especially when the equation of the reaction involves gases. Now we're going to take our moles, 0.0259 moles of oxygen gas. We got the ratio from the balanced equation, 3 moles oxygen, 2 moles potassium chlorate. And then finally, we'll get this out of moles, potassium chlorate, and into grams. 1 mole should have the molar mass. If I add it up on my periodic table, I'm going to go like 122.55 grams per 1 mole. There. Plug it in. And I'm going 2.12. grams of potassium chlorate. So really it's kind of like those stoichiometry problems that we had looked at earlier. I think there was a combustion one. But this time, before we could do any PerfNerd or any kind of calculations, we had to subtract off the pressure coming from the water vapor in that container where the gas was collected. Other than that, there's nothing that could make this Dalton's law of partial pressure any more difficult for you.